Here's this example problem that reads, find the output voltage and theoretical conversion efficiency of an oxygen-hydrogen fuel cell operating at 298 Kelvin. Oxygen is supplied from air at 1 atmosphere, and all other products and reactants are also at 1 atmosphere. Here we have a table that gives the change in enthalpy and change in Gibbs free energy for water at 1 atmosphere at selected temperature. So basically what's happening is that that's giving us the delta H for the reaction and the delta G for the reaction that produces water, right? The reaction of hydrogen and oxygen produces water. So in this case, our voltage, right, would be quantified as Gibbs free energy from the reaction divided by the number of moles of electrons times Coulomb's constant. So we get here, again at 298 Kelvin, we get Gibbs free energy as 2.29 times 10 to the 5th, that's kilojoules per kilogram mole, divided by the fact that we get 2 electrons out of the hydrogen-oxygen reaction times the constant 96,500 coulombs per mole. In that case, our reference voltage of 298 K would be 1.187 volts. Now, I always get questions of how do I know I got 2 electrons? Because, well, this reaction to get water, right? I have hydrogen plus 1/2 mole of oxygen yields water. And that is done according to a half reaction, right? So this reaction of 1 mole of hydrogen and 1/2 mole of oxygen is actually split to, I basically get 2 electrons from the dissociation of the hydrogen and 2 positive ions from the hydrogen reacting with my oxygen to produce H2O. So again, I get 2 electrons based on the 2 half reactions that we talked about, and that's what becomes this number of electrons here. Going from there, I wanted to go ahead and take this voltage and correct it for the partial pressures given in the problem. I would get that my actual voltage would equal this reference voltage minus the correction for the partial pressures that the reaction occurs at. So again, on the numerator, I get my partial pressure of the partial pressure of the one reactant product raised to the number of moles of that product multiplied by the other product partial pressure raised to its number of moles divided by the same thing for the reactant side. So if I were to go ahead and get this equation into a form appropriate for this problem, I'm not going to fill in all the numbers, but what I'll do is at least set up the equation for this problem. Oh, sorry, insert natural log there. I would get, in this case, on the product side, I have 1 mole of water, excuse me. So again, the partial pressure of water raised to the number of moles of water, so that would be one atmosphere of water, divided by the partial pressure of hydrogen, so that's 1 reactant that I have, raised to the number of moles of hydrogen, so that would be partial pressure of hydrogen, which in this case is 1 atmosphere, raised to the number of moles of hydrogen, which is 1, multiplied by the partial pressure of oxygen, raised to the number of moles of oxygen, which is 1/2, right? And the partial pressure of oxygen in this case would again be probably if it's supplying the oxygen from 1 atmosphere of air. So if you look at the constituent gases in air, in this case, the partial pressure of oxygen would be 0.2, which I think represents 20% of the content of air is oxygen. So that would actually be 0.2 raised to the 1/2 power. If you go ahead and carry out that math, you would end up that the actual voltage that you get would be 1.177 volts. All right. The next part of the problem is asking for the efficiency, the theoretical efficiency, again, which would be the change in Gibbs free energy over the change in enthalpy, right? And again, that would be at the reference point. So if I go ahead and I try to compute Gibbs free energy for this equation, it would equal the reference, at the reference reference Gibbs free energy plus the correction for the operating temperature and pressure. So here we have on the numerator, sorry, I was about to write in oxygen, but it's actually the inverse it's the inverse of what it was for the voltage, because we have here the reactants on the numerator and the product on the denominator. So you have the partial pressure of hydrogen raised to the number of moles of hydrogen multiplied by the partial pressure of oxygen raised to the number of moles of oxygen divided by the partial pressure of hydrogen raised to the number of moles of, sorry, the partial pressure of water raised to the number of moles of water. In that case, we would get the change in Gibbs free energy to be 227,100 kilojoules per kilomole. And in this case, we would get so we would take that 227,100 kilojoules per kilomole divided by the reference change in enthalpy, which at 298 Kelvin, which is the operating temperature of the fuel cell, would be 242 or 2.42 times 10 to the 5 kilojoules per kilomole. So that would be 242,000. And that would equal 0.938 or 93.8%. So what's interesting though is that that's the efficiency, assuming that the water stays liquid. If it were to actually convert to water vapor, convert to gas, you would have to go ahead and compute what is called the higher heating value as a function of the lower heating value, which basically just says that I am going to take this 242,000, right? The 242,000, that would be the kilojoules per kilomole, the change in enthalpy of the reaction, and I'm just going to go ahead and add the enthalpy of vaporization. In that case, I would have a change in enthalpy of 286,000, and that would change the efficiency. So I have the same change in Gibbs free energy, but I would divide it by a different enthalpy, or change in enthalpy of the reaction due to the fact that water changes phase, and that would affect my overall efficiency and bring it down to just under 80%.